In the introduction, we determine the slope of a line that represents the relationship between distance and time when driving at a constant speed. By finding the slope of this line, you found the derivative of the function. But this linear function represents a constant speed, when in reality, it is more likely that your speed will vary over time, which will cause your graph to become nonlinear. In fact, when plotting real-world data, you are much more likely to be dealing with a nonlinear function than with a linear function. So, how do you determine slopes and rates of change for data that is not represented by a straight line? The answer is you use a limit to find the derivative. The next question is, what are we going to find the limit of? And we need to cover a few more items before we can answer that question. Take a look at this graph of a linear function. Is the rate of change constant? Yes, a straight line has a constant slope and hence a constant rate of change. Now take a look at this graph of a non-linear function. Is the rate of change constant? No, this graph is not a straight line, so the slope and hence the rate of change is not constant. Note, for this section, we assume that we are dealing with continuous functions that are differentiable at all points. Later, we will discuss some functions that are not differentiable at all points. At any specific point on a graph, the slope of the curve at that point and the slope of the tangent at that point are the same, and a derivative is used to determine that slope. The derivative is also used to determine a function's rate of change at a specific point. This may sound confusing, but it's simply a matter of perspective, as the slope is the rate of change. The slope varies as we move along a nonlinear graph. Let's draw a tangent at each of the given points on our graph. The slope of the curve at point P is the same as the slope of tangent 1. The slope of the curve at point Q is the same as the slope of tangent 2. The slope of the curve at point R is the same as the slope of tangent 3. You saw that the slope of a nonlinear function at a point is the same as the slope of the tangent line at that point. But what happens if the tangent is a vertical line, as in this graph? A vertical line has an undefined slope, so how can we use the vertical tangent to determine the instantaneous rate of change at a point? The answer is we use infinity and negative infinity. You'll learn more about this in a later module. Some nonlinear functions will have no tangent line at a given point. For example, the graph on the left represents a step function which has no tangent line at the endpoints of each step. The graph on the right is an absolute value function which has no tangent line at the sharp curve where the graph changes direction. Before going further with tangents, slope, and instantaneous rate of change, it is important to understand average rate of change on a nonlinear function. On a linear function, this is simple, as both the instantaneous rate of change and the average rate of change are the same. They are the slope of the line. So, how would we determine an average rate of change on a nonlinear graph? Let's place 2 points on this graph and draw a line through them. What is this line called? That's right, it's a secant. To determine the average rate of change on the open interval between points P and Q on our curve, we simply need to find the slope of the secant using our slope formula. The slope of the secant is the average rate of change. The slope of the secant is 1 over 2, and the average rate of change on the interval is 1 y unit per 2 x units. For instance, if y represents distance in miles and x represents time in minutes, then the average rate of change on the interval is 1 mile for every 2 minutes. Let's say we want to know the rate of change at point P marked on this graph. If we were to draw a line tangent to our curve at P, the slope of the tangent line will give us the rate of change at point P. But how can we be sure that we are drawing the tangent precisely? And how can we determine the slope of the tangent when we only know one point? Furthermore, how can we determine the equation of the tangent line? This is known as the tangent line problem. So what can we do? Let's add some secant lines that go through P. Since each secant intersects the graph at 2 points, we can determine their slopes to find the average rate of change on each of the intervals. The slope of the red secant is the average rate of change between points P and A. The slope of the purple secant is the average rate of change between points P and B. The slope of the gold secant is the average rate of change between points P and C. Notice that the slope of the secant lines is changing as we move closer to point P. We could continue drawing secant lines, moving the second point closer and closer to point P, and the slope of these secants will approach the slope of the tangent at point P. What concept are we referring to here? I hope you said the limit. The slope of the tangent is the limit of the average rate of change. To be certain that the limit exists, we should check from both directions. Remember, we only have a limit if the one-sided limits from both the right and the left exist and are equal. In this graph from the previous example, we can see that we do have a limit. If a limit only exists from one direction, or if the one-sided limits are not equal, then the derivative does not exist at that point. Examples of when this happens include at a point of discontinuity, at an endpoint, and at a sharp turn, such as in the absolute value function. Using the derivative to find the slope at a given point not only tells us the instantaneous rate of change at that point, but also allows us to solve our tangent line problem. Using the slope and the point of tangency, we can calculate the equation of the tangent line using the point-slope form. We will do this in the next lesson. Throughout this module, you will encounter the terms derivative, differentiable, differentiation, and differential. It can be confusing, so here's a simple definition of each term. Derivative refers to a rate of change of a function. Differentiable. If the derivative exists, then the function is differentiable. A function is differentiable at a point if the derivative exists at that point. A function is differentiable on an open interval if it is differentiable at every point in that interval. Differentiation is the process of finding the derivative of a function. Differential refers to the actual change of the function. You learned in the module on limits that for a limit to exist at a given point, the function must be continuous at that point. You learned in this lesson that a derivative only exists if the limit exists. This leads us to the following theorem. Differentiability implies continuity. If a function is differentiable at x equals c, then the function's derivative is continuous at x equals c.